Hello! In this series we're gonna talk about number theory over the integers and over the polynomial ring. I'll mainly talk about lattices and continued fractions and also applications to coding theory. And yeah, so let's get started. So we're gonna start with Dirichlet's approximation theorem. I'm gonna assume Minkowski's theorem from the theory of lattices, but this the approximation theorem is just for motivation, so maybe I'm gonna make at some point a video about Minkowski's theorem, maybe not, let's see, but this video here is mainly for motivation, and we'll continue and then also see analogies over the polynomial ring. So let's state and prove the theorem. Assume we are given a real number and a positive integer, and the claim is that there exist two integers where p should be the numerator and q should be the denominator, and we have bounds on the denominator. It should be non-zero, should be positive, and bounded by n. And now we want to see how good can we approximate alpha, and the claim is that we can approximate it at least so good that we get an error of less than 1 over q times n with numbers which have denominators, rational numbers with denominators bounded by n. And so let's prove it. As I told you, the idea is to use Minkowski's theorem from the theory of lattices. As I said, I'm not going to prove this for now. And so we don't need the more precise bounds on the successive minima, but it's enough to have the statement about a non-zero lattice point inside a convex symmetric body. So what we want is we want that, let's rewrite it, just let's multiply by q, alpha q minus p is less than 1 over n. And now let me first be a little bit crudely and not prove it completely, but just tell you how you can then really prove it. So let's consider the set as follows. So we want a convex symmetric set which has large enough volume, and since we want these two integers q and p as our lattice, we will just consider the lattice which consists of pairs of integers, c squared. So the set we consider is the set you would imagine. We want to have, first of all, a bound. So we will consider, of course, pairs of real numbers, and we want a bound on q, and we want this. And so for the bound on q, we will say, okay, the absolute value should be bounded by n. And for the second condition, we say we want alpha y minus p should be less than 1 over n. Okay, that's our set. it is convex, or it is a convex symmetric, where symmetric means around the origin. It's a convex symmetric body that I'm probably gonna show you in another video, but it's true. And S has volume given by the following. So we have y ranges from -n to n, then alpha y, I wrote a p here, sorry, this should be of course an x, alpha y minus x, and x now ranges from alpha y minus 1 over n up to just rewriting the condition here, and from alpha y minus 1 over n to alpha y plus 1 over n, and that's where x ranges, and then we just have to integrate the constant 1 function dx dy, and so both of these integrals are actually easy to evaluate. So the inner one we just have a length of 2 over n, and then we get a dy, and now this one has length 2n, so we get overall a 4. We will see in a moment that we want something bigger than 4, so now let me tell you what are the small changes you have to do. So we will change we want something bigger than 4, so we will do a +1/2 here, because when we're looking for integer pointers, +1/2, we could also add something else, doesn't really matter. This won't really hurt us, and let's call it s tilde, and then what this will do, this will replace the equals 4 by a greater than 4, and this is what we want. So then we get that the volume of S is greater than 2 to the 2, which is 2 to the dimension is 2, times the determinant of our lattice, or co-volume of our lattice, and the lattice we consider is the lattice of integers, just the integer entries, and so this has determinant 1, so we get this statement here, and applying Minkowski's theorem, we get a non-zero lattice point, so a non-zero PQ, which is inside our lattice and inside S. And now we still have to argue why can we assume that Q has lower bound 1 and is at most n. So since minus P minus Q is also in here, we can assume that Q is non-negative, and if Q was 0, then we would get, where's our condition? We have this, alpha q minus p is less than 1 over n, so then we would get that the norm of p was less than 1 over n, but p was an integer, and so it would have to be 0, but we assumed the point pq is not the 0 point, so this gives a contradiction. And this then proves the claim. This proves Dirichlet's theorem. And next time we're gonna reinterpret it a bit. We're gonna show actually that the set S, or actually I should write S tilde here because we changed it a bit, so that this set is actually convex and symmetric. We're gonna change a few things, and then we're gonna show how to use lattice reduction to find such a thing. There's also another way to find it. This is using continued fractions, and we're also gonna talk about continued fractions soon. And yes, that's it for today, and at some point we're also gonna talk more about the case of polynomials and the analogies between the integers and polynomials. So thanks for listening, have a nice day, and bye.